Hi folks, Mr. Long here, just going to do a quick screencast on max and min on intervals, so like absolute max and min. So similar to what we did yesterday or recently with polynomial functions. This time we're going to do it with exponential functions. And we're going to do this staged. So today is going to be about reviewing the skills that you need to be able to do that. So there's two main things you need to be able to do, right? So if you want to get the max and min on an interval, and so think of, a function like this, right? If you want to get the max and min on a certain interval, you need to be able to get that location right there. X equals CP, a critical point or critical value. So you need to be able to get that. So how do you get that? Well, there's two parts to it. One, you have to get the derivative. And then secondly, you have to set the derivative equal to 0 to know that you're at a maximum or minimum. So what derivatives do we need to do if we're going to work with exponential? Well, we're going to focus on ln and e. We're going to focus on the product rule and the quotient rule. Okay, those are the derivative rules and the derivatives that we need to be able to do. The second thing you have to be able to do is to solve equations. And because you're going to have to set that derivative equal to 0, y prime, the slope function. So you're going to have to do a bit of common factoring and solving equations with ln and e. So we're just going to review that fairly quickly right now. And so let's go through it. So here are our examples. And what I'm going to do is just go through and annotate. I've already done the derivatives, and so you'll see I'll circle the original question first. So there's our original question. What is the derivative of e to the x? Well, do you remember the rule for that? D by dx, e to the x is just e to the x, right? It's its own derivative. Now, what happens if there's not an x there, but there's a 4x there? That's a chain rule question. Okay, it's a chain rule question. So I have to differentiate that exponent. That's the inside function. And with these ones, I don't write out the full chain rule because it's so quick to do. So the derivative of 4x is 4. So it's going to be that 4 multiplied by that 5, which is going to work out to 20. So 4 times 5 is 20, and then I just repeat the exponential part, e to the 4x. Okay, so that's how you do derivatives of e. What about derivatives of ln x? Well, this 7 is just a coefficient, so I'm just going to multiply that in. So I have 7. Oh, and again, by the way, you might want to pause, record it down each time so you have a set of notes. So 7, and then we multiply by the derivative of ln x. The derivative of ln x is 1 over x, right? So then at the very end, I have to do 7 multiplied by 1 over x. 7 times 1. 7 times by 1 is 7, and then it's over x. Okay? We're going to change this just a little wee bit. Okay, just a little wee bit, and you're going to notice something strange here. So we're going to do the derivative of 7 ln of 6x. How do we get the derivative of 7 ln of 6x? Well, now I have 6x inside there, so it's a chain rule question, right? I have a function inside a function. So the rule for derivatives of, so d by dx of ln of, let's call it g of x as our inside function, is just g prime of x over g of x. Okay, so that's the derivative of a ln function. Take the derivative of the inside, which in this case is 6. That goes in the top, and then the original inside function goes in the bottom. So it becomes 6 over 6x multiplied by 7. But we can see the 6's divide out nicely there. So you get 7 over x. So in fact, the derivative of 7 ln x is the exact same as the derivative of 7 ln of 6x. That's quite interesting. And you can prove that with the product rule of logs. Okay, speaking of product rule, not of logs, but of derivatives. So we're going to do some product rule questions, or a product rule question. So this one is ln x multiplied by sine x. And you remember with the product rule, we have a and b, the two parts of the product, the two factors. And the way we're doing it now is, because the formula is a prime b, ab prime, what we want to do is write it that way, right? So we want to write it this way and this way. So the first thing that you would write down is a equals ln x. Then you'd move up and to the right and write b equals sine x. And then you differentiate. So we know that a is ln x, b is sine x. So a is ln x, go up and do the derivative here, it's 1 over x. Start here with sine x, do the derivative, b prime, it's cos x. And now you import those values into the product rule. So what I've done here is, oh, actually we can look right here. So here we multiply these together. So 1 over x multiplied by sine x. Well, what's 1 over x multiplied by sine x? 1 times sine x is sine x over x. So it's sine x over x. Check. Then the next one is just ln x times cos x. Okay, and that's it for your product rule. Again, process. Identify each factor, a and b. Then write, you can set up like a grid like this, a prime, a, b, b prime. And you start by writing a and b, and then you do your derivatives. You have to go up to the derivative of a, you have to go down to do the derivative of b, and then it's a prime b plus a b prime. Fairly straightforward. Okay, the quotient rule. Whoops, let's go down to here for the quotient rule. And I know I'm going through these fairly fast. So the quotient rule. How do we do the quotient rule? Well, the first thing I want to share with you, this one looks like you would do a product rule to that, right? But I want you to think of, if you have the number 3 to the negative 1, what's another way of writing that? 1 over 3, because it means 3 divided by 3 once. That's what 3 to the negative 1 means. So if you notice then, what would e to the negative x be? E to the negative x is just 1 over e to the x. It means divide by ex times, right? That's what negative x means. In an exponent, divide by ex times. So we can write it as 1 over e to the x. So I avoid, whenever I can, negatives in exponents. I just find it's easier, there's less mistakes. So what I would do is, for this, I would simply rewrite it this way. Okay, rewrite it that way. So it becomes x cubed over e to the x. Okay, x cubed over e to the x. And what we want to do is, and we do that so again we can avoid negative exponents. Now it means I have to use the quotient rule, which is a little bit more difficult, but honestly it's not that much worse. So again, look at our formula right there. And it's really exactly like the top part is very similar to the product rule, except there's a minus sign there. Top prime bottom minus top bottom prime. Again, do it the same way. Okay, the same way. Now, oops, I made a bit of a mistake here, didn't I? That should have been top, prime and top, bottom and bottom prime. So we write down top first, bottom, right? You do that first in the diagonal, and then you do your derivatives. The derivative of x cubed is 3x squared. The derivative of e to the x is e to the x. Okay, so then we import that into our product rule, or quotient rule, which you can see right there. Top prime, bottom, minus top, bottom prime. All over the bottom, squared. Now, something's interesting here. So I'm supposed to square the bottom. The bottom is e to the x. So instead of writing e to the x squared, I write e to the x times e to the x. I think you're going to see why this is true in a second. So let's do this and let's factor it fully. So let's see if we can identify some common factors here. So I see an x squared and an x cubed. Well, what's the greatest common factor? So what's the highest shared exponent? X squared. That's a common factor. E to the x and e to the x. That's a common factor. So what we're going to do is factor that out of the numerator, x squared and e to the x. Okay, so I factor out x squared. Oops, that means I'm dividing by x squared, everything that's in those brackets. And I'm also dividing by e to the x. So if I look at this right here, I have to divide that by x squared and e to the x. Well, the only thing that's going to be left is 3. Then in the second set of brackets right here, or the second term, I'm dividing by x squared. X cubed divided by x squared is x, and e to the x divided by e to the x is 1. So the only thing I have left is 3 and x. Now, if you notice something, we factored out e to the x. So notice that I've got e to the x here, and then I've got an extra e to the x down there, so they can both divide out. So that your final answer is going to be y prime equals x squared 3 minus x over e to the x. Okay, folks? So you want to be able to simplify the quotient rule in that form. All right, let's solve a couple of equations. So again, pause, rewind, go through everything. So we're going to solve this equation right here. So 4x cubed e to the x plus x to the fourth e to the x, and I need to solve that. So do I have common factors? Again, it's very similar to the last question that we did. E to the x is definitely a common factor. And also x cubed, x to the fourth, so the greatest common factor is x cubed. Okay, so e to the x comes out. That gets rid of that and that. X cubed comes out. That gets rid of that in 3 of those 4. So I'm left with e to the x, x cubed times 4 plus x equals 0. Now, I have, it's called zero factor property. So there are 3 factors here that we're dealing with. 1, 2, and 3. And any one of those could be 0. CF stands for common factor, by the way. If you've seen the solutions, PR means product rule, QR is quotient rule. So let's look at that. So e to the x, is it ever 0? Well, draw a graph. Remember that refers to a y value. There's your graph. It's asymptotic. So it never is 0. So there's no solution for e to the x equals 0. What about for x cubed equals 0? Well, it's 0 if x equals 0. What about 4 plus x? 4 plus x would equal 0. X would be negative 4. So if this were a derivative, that would mean that x equals 0 and negative 4 would be the critical points or critical values, right? That's where the tangent slope is 0. Okay, so that's like a product rule question that you've had to factor and solve. Okay, what about this? Here's a log one, or a ln one. We're gonna solve this ln equation. Now, what I really like to do is to always have a picture of what ln x looks like, right? Because eventually I'm going to simplify it down to ln x equals a number. So I know that ln x, just like all log functions, has an x-intercept of 1. Okay, I know that, and it goes nice and smoothly here. So if you notice, to the right of 1, the y values are positive. To the left of 1, the y values are negative, right? That's an important dividing line there. All right, so here's the equation. Negative 2 ln x minus 3 equals 0. So just basic inverse operations to begin. So because of that minus 3, I'm going to add 3 to both sides. And then because of that minus 2, negative 2, I'm going to divide both sides by negative 2. And I end up with this. Ln x equals negative 1.5. How do I solve that? Well, when I have a ln equal to a number, or a log equal to a number, I rewrite it, or represent it again, but with an exponent. So remember that ln just means log to the base e. So if I have log of x to some base e equals y, how do I rewrite that with an exponent? Well, the base is e. The exponent is y, and the evaluated power over here is x. So I take this and I rewrite it. The base is e, the exponent is negative 1.5, and the evaluated power is x. So now that isolates x. So again, take your ln or log and rewrite it with an exponent. So I know that that's e repeatedly divided by negative 1.5. Oh, by the way, ln x equals negative 1.5. If I go over to the graph, that means that the graph of ln x, so the equation that I'm solving is ln x equals negative 1.5. So what I'm really looking for is where do ln x and then the horizontal line negative 1.5, where do they intersect? Well, since it's a negative, right, it's going to be, my solution has to be in between 0 and 1. Okay, because this is a negative. And that's a good way to reason out and see if your solution is correct, right? If it was ln x equaled 10, you're going to be up here on the curve and you're to the right of 1. So let's see what happens here. So e to the negative 1.5 is x. And if you represented it at the end with only positive exponents, it would be 1 over e to the 1.5. If you put that in your calculator, it works out to about 0.22, which does seem reasonable, given that our solution's got to be between 0 and 1. Okay, so that's a quick review. There's nothing in there that we haven't already done in that review, but nonetheless, you'll need to do that. So today's homework is going to be just to get critical values. So for example, you would do something like this. Say it was, I won't do one with e and ln, that's what's going to come. So you're going to start with an equation. Say y equals x sine x, for example. So then what's the first thing you're going to do? Well, you're going to state that I want y prime to be 0. This is to get critical points or critical values, okay? Which is the x value where maximums and minimums can occur. So the first thing I want to do is set y prime equal to 0, and that's to get our critical points. Then I actually have to get my derivative. Now this I would use the product rule, a and b. A prime b is sine x, because a prime is 1, plus x cos x. Okay, x cos x. And then, so you have your derivative. Oh, whoops. That shouldn't be y prime equals. We wanted to make that word 0. So it should all be that equals 0. Okay, so in this case, now what's weird about this one is this one we can't solve very well algebraically. All the ones that I'm giving you, you'll be able to, I think. But if we had to do this one, this is a really interesting one. So I would have to go subtract sine x from both sides. And I end up with x cos x equals negative sine x. And then I would divide both sides by cos x. And I would end up with x equals negative tan x. Or negative x equals tan x. Now there's no amount of algebra in the world that'll allow you to do that, so that's something you'd have to solve on Desmos. So I don't know if you remember what tan looks like. It looks like this, and it's asymptotic. And then you'd have negative x coming down like that. And so we definitely know that one solution is x equals 0. That one we can figure out quite easily. And then there'll be a whole bunch more solutions because it just repeats, right? Just keeps repeating. So where the next solution is, I'm not sure. But anyway, you get the idea. Okay, so there's one solution at x equals 0. So, and though that would be a critical point. Okay, that would be a critical point where there's potential to be a maximum or minimum. Again, what do? Get the derivative. Set the derivative equal to 0 and solve for x. Okay, and it's going to be all logs exponential, a little bit of trig as well. So get the derivative, set it equal to 0, solve for x. And then tomorrow we're going to add in determining the actual y value, so in the endpoint, so we can get the absolute max and min on an interval, and also maybe draw a sketch a little bit. All right, folks, so hopefully that review helps and you'll be able to do these questions now.